So in this lecture, we're going to transition from talking about neurons to talking about computational systems, artificial systems, that were created in a way that mirrors many important properties of neurons and that help us to better understand how neurons and neural assemblies can be computational devices. Nowadays, they're usually called neural networks, and we'll talk about them in a sort of general way in this lecture, and we'll talk in some more specific ways in the next. We're going to start off just by talking about neural networks in terms of their components and their sort of general architectural features. Then we'll talk about how they go about representing objects, properties, and relations out there in the world. And then we'll talk about how they process, how they compute, and how they learn. So we're going to start off then by talking about neural networks, components, and architectures. And we'll start by talking about individual nodes or units in those systems. And we'll talk about them specifically by talking about their properties, comparing those properties with the properties of neurons. Then we'll turn our attention to systems, to collections of these individual units or nodes, and how they're organized often into input layers, output layers, and hidden layers. And then we'll talk about their interconnectivity between these different layers. Neural networks were really created to come up with a type of computing device that mirrored the basic functional operations of individual neurons and the nervous system generally. They have individual units that are said to correspond to individual neurons or populations of neurons. So when we look at these individual neurons, we want to see how they compare in a sort of systematic way. What is it they are trying to model about the functioning of neurons? And so, like their biological counterparts, these neurons have connections with one another that allow them to receive input and output. For our neurons, it's neurotransmitter receptors on the dendrites that allow a neuron to receive information about the firing rates in other neurons by changing the membrane potential, postsynaptic membrane potential, in response to the activity of those other neurons. These changes can be either excitatory or inhibitory. They can depolarize or hyperpolarize the localized membrane on that dendrite. Similarly, these individual neurons have input connections that transmit a weighted output value from the previous neuron. Input values can be either positive, which would correspond to excitatory, and negative, which would correspond to inhibitory. Thus, for any time period, call it T1, each of the weighted input connections to our typical neuron models the total changes in membrane potential in response to all the synaptic binding resulting from all the neurotransmitter released by another neuron during the time period assigned to T1. Now, recall that at the cell body, where we have the emergence of the axon hillock, activation is summed in that area so that the net excitatory and inhibitory input to all of the dendrites that filters into the cell body can cause an action potential, an all or nothing event that occurs when the net activation depolarizes the membrane of the neuron beyond the threshold. We have a similar function with our individual neurons. They too can sum positive and negative input and generate an activation value in accordance with their activation function. Thus, the activation for any neuron is going to be the value for some particular time that models the action potential, the firing rate at the axon hillock for some time period assigned to that T1. Now, our neuron has these axon terminal fibers end in synaptic end bulbs and that transmit these all or nothing signals traveling down the axon from its presynaptic terminals to the postsynaptic terminals of the next neuron. it does so by releasing neurotransmitters in relation or proportion to the firing rate, that is, the number of action potentials traveling down that axon. In our neural network, those individual neurons are going to have output connections, which transmit weighted output values as determined by the level of activation, and it will then translate that output value to the other neurons. Thus, for any given time, each of our weighted output connections models the total changes in membrane potential in the next neuron in response to all the synaptic bonding resulting from neurotransmitter release from the neuron that individual unit models for some period of time, T1. So we've taken a look at individual neurons, and we've seen how they function and how their function relates to the functioning of individual neurons. Now we'll sort of briefly discuss how those individual neurons are organized. So they're organized to create computational models or systems in the same way that our brain is organized. That is, we are collections of these individual neurons interconnected together to serve as a single computational system within our overall brain or nervous system. And these neurons are the same way. So like their biological counterparts, they're organized into systems, neural network models. And two common ways that they're organized are in terms of input and output layers in a two-layered network. Another very common organization is a three-layer feed-forward network, and this is a schematic drawing of that. Here you have a set of input nodes. They feed their input, their activation, into a set of what are called hidden units. They take their activation and then compute an output that they send to individual nodes in the output layer. And note that each individual neuron is at least potentially connected to every other neuron at the next level in these systems. And so you can have more complex or Baroque systems. You can have feed forward, you can have feedback, you can have recurrent network systems. There are all sorts of different ways you can arrange them, but ultimately it's a set of individual units that are highly interconnected with one another.